In this video, we will continue seeing several features of the optical block. We will start this video by explaining the aperture and we'll end it by describing the depth of field. Regarding the aperture, is a physical hole opening through which the light travels to the camera, to the sensor. Sometimes the aperture is referred specifically to the diameter of that physical aperture. This will be a wide aperture and this will be a quite narrow aperture. The aperture not only determines, as expected, the quantity of light incoming to the video sensor, but also has implication in how collimated the admitted incoming rays are. And this is very important regarding the image composition. The appearance of the object appears in that image relate because the objects can be more sharp or less sharp depending precisely of the diameter of the aperture. For example, if the aperture is narrow, then only highly collimated rays, highly coherent rays are admitted, and this results in a more sharp focus of all the image. But if we have a wide aperture, then uncollimated rays and coherent rays are admitted, resulting in that only a part of the objects in a specific depth in the scene, a specific range of depth in the scene, will be correctly sharp, will be correctly focused, and the other will appear blurred, as is indicated, for example, in this figure. Okay, a wide aperture will impact in the sharpening of the different objects in the scene, and only one part of the objects can be correctly focused. On the other hand, with a narrow aperture, all the objects can be focused correctly, and all of them will appear to be sharp. Okay. Also, the aperture has implication, as we have said, in the quantity of incoming light. That will be explained this soon. This is an example, a real example about using different aperture diameters and the observing appearance of the image. We see that with in this case, this corresponds to a high aperture, a high diameter aperture, indicated by this number that will be explained later. It's called F numbers, and it will be explained soon. And if we have a wide aperture, as you can see, only certain objects, in this case the girl, can be focused adequately, and all the rest of the scene, in this case the background, are blurred. On this effect of sharpening and blurring of different objects in the scene change gradually according we are narrow and narrower the aperture, the diameter of the aperture, until having a very narrow aperture in which all appear acceptably sharp in the image. The other perspective of the aperture is, of course, the kind of the amount of incoming light, incoming rays that are admitted by the sensors. Of course, with a wider aperture, we will have more light incoming to the sensor, and for certain scenes with having a very low sources of light, it will be necessary to have a wide aperture, like indoors, or even despite of indoors with a very low sources of light, like in this example, a candle. All of this, of course, is regarding to the given exposure time, the time the sensor is open to admit rays. So for a fixed given exposure time, we need a wider aperture for under low light condition, and vice versa. Given that fixed exposure time, we will need, or always will be necessary, a narrow aperture if there is much light in the environment, like a sunny open area. In the case of the human being, this modulation of the incoming light is accomplished by the pupils. In most modern or professional cameras, we can modulate aperture by means of a device that is an adjustable diaphragm called iris that modulate the aperture. The aperture can be defined by as the quotient between the focal length and the physical diameter of that aperture. And usually only a subset of possible f values are considered, like 1.4, 5.6, 11, etc. And you can see that lower numbers implies wider aperture and vice versa. Higher f numbers imply narrower apertures. The real meaning of this, well, the precise figures of depth numbers are because they are related between continuous values of f numbers in such a way that continuous values of f numbers means that we have the double or the half of the amount of light towards the camera sensor. So these somewhat strange numbers, because they are not appearing, they don't follow a specific pattern, are the result of the fact that between two f numbers, the quantity of light is double if we are widening the aperture, or just halving the amount of light if we are closing narrower the aperture. In professional environments, like the one that we are considering for professional TV broadcasting, in addition to depth number, are used the T numbers. T numbers are related to the transmittance, the capacity of radiance transmittance of the material. In this case, the purity of the crystal that compose the different lenses. And according to that, we can define mathematically the T number as the quotient between the F number and the root square of the transmittance. Another feature of the optical block is the depth of field, that is also very related with the aperture. We can define the depth of field as the distance between the nearest and the farther objects in the scene that can be acceptably sharp in our image. Okay, so in this image, the depth of field will be defined in this range, where the objects are acceptably sharp. Okay, sometimes depth of field is also called focus range or effective focus range. How is the relation with the aperture? Well, if we have a lower aperture, that means that many incoherent and collimated rays are admitted, the depth of field will be narrower and narrower, and vice versa. With narrow apertures, we have increasing values of depth of field, meaning that all the objects in the image will be becoming more and more sharp. According we are narrowing, closing the aperture of the camera. Physically, we can see this see this effect of what kind of objects can be sharp or focused in the image with this representation. Here we have a certain aperture that allow to pass some very collimated rays that will be the I'm going to try to draw a straight line. Okay, like this. Well, just imagine that this is a perfectly straight line. This will be, and perhaps some right close to this. So the most straight lies between the object emitting the light and our image sensor. Those are the very collimated rays. But there are also others that are not so collimated, more diverging. Our lens have the capacity to blend those uncollimated rays to just be focused in one point. In this case, this will be the point in which all the rays are collimated, are focused, are concentrated. But the lens has only that ability to blend correctly certain part of the uncollimated rays in the scene that coming from a specific depth, from a specific distance between the lens and the real world. It's unable to blend correctly, to focus all the rays from coming from all the different objects at different depths, at different distance from the lens. So in this case, for example, as you can see, there are some objects that are correctly focused in this range, and others that are not correctly focused because the lens focused just before or just later the plane sensor, and in the image will appear just blur.